Constraints preserve system security, ensuring if any single transmission asset is lost, the remaining assets do not overload. Thermal constraints are designed so that if a parallel circuit trips, there are at least 15 minutes to remove the overload before the remaining in-service line sags to the minimum clearance height. Let's start with an unconstrained grid. The marginal price is $100. The generator at bus X offers 100 megawatts at $80, which is below the marginal price. There is an 82 megawatt load at bus Z, and the excess generation goes to the rest of the system from bus Y. A constraint has been built in the market system that protects lines A and B from overloading each other if the other one trips. The constraint in this example is A plus B must be less than 60 megawatts. 60 megawatts is the right-hand side of this equation. Since the total across A and B right now is only 32 megawatts, all load at bus Z is supplied unconstrained. Let's have a look at a similar scenario. The marginal price is still $100, but this time the generator at bus X offers its 100 megawatts in two tranches. Only 50 megawatts of generation is offered below the marginal price. So the remaining 32 megawatts needed to supply the load at Z are supplied from a cheaper generation at bus Y. Constraints are based on modelled power system conditions. Forward schedules show when the market expects constraints to apply and the limit. In real time, system conditions may be different, so constraints may need to be adjusted to resolve real-time violations. As a result of a real-time adjustment, there will be change to the generation pattern compared to what is forecast in the forward schedules. The constantly changing power system means system coordinators regularly monitor the right-hand side of constraints to ensure accuracy. In this case, a real-time N-1 violation exists. A decision is made in real time by the system coordinator to update the right-hand side for the constraint on A plus B from 60 down to 52 megawatts. This means A plus B is now a binding constraint. To relieve the binding constraint, the flow on A and B is reduced by 4 megawatts, so an additional 4 megawatts are needed from the generator at bus X to flow down circuit C to supply the load at Z. To get this extra 4 megawatts down circuit C, 8 megawatts is required from the generator at bus X. This means more power flowing down D and E, so the generation at Y will also be reduced due to the constraint. The extra megawatts from the generator at bus X are in the next price tranche, which sets the local bus price higher at bus Z. Let's look at how applying discretion in this scenario can impact the market. The grid is unconstrained and the market is solved for optimal economic dispatch. A discretion is applied to lower the right-hand side of the constraint to 52 megawatts. The grid is now constrained and some high-priced generation is required from the generator at bus X. Not all of this higher-priced generation is required by the market constraint. When the constraint is applied, part of the generation that was offered in the higher price tranche moves to the bottom of the merit order, causing a price separation. This higher price generation is constrained on. However, due to the price separation, some of the generation at Y is no longer in the price stack. This drops the marginal price down. In this case, the marginal price is lower for the unconstrained side of the grid. The grid remains unconstrained until the inputs change and the constraint no longer binds.